And we have Mike from the camera, Steve.
Yes, we do.
So
You are live, and I can see you.
present, share screen.
Sup, people?
Oh, there you go.
Zak Klein.
Alrighty.
There we go.
You're on, Mark. You want to open us
All right,
up?
started my screen share.
He's right.
I'm on while you're working on it. I should.
He's
You're
live.
good. You're good.
All right, Benjamin, come here.
Oh,
Come here.
now you're in trouble.
Here, turn around, face the camera.
Yeah.
My grandson wanted to be on camera. Okay, that's enough.
Come on!
Well, folks, welcome to our August meeting. Those of you who are joining us online, and we have a group now on the east side that is meeting at Skyline Church in O'Fallon, Illinois. Our friend Josh Lowry lined that up, so they have a group that they're going to get started over there. So Josh and everybody over there, thanks for joining us tonight, and all the rest of you who are viewing online as well. Couple things to tell you about before I introduce the speaker. First of all, the Creation Research Society had their annual conference here at Missouri Baptist University 2 weeks ago. And we actually had two of our board members, one Zak Klein, who will be speaking tonight, and the other Hannah Klein, that presented papers at this conference. And of course, you present your paper and your analysis, and then you're on the hot seat with people asking you questions and what have you. So it was rather interesting, but what was interesting is they allowed us to set up, first of all, a table in the lobby. And the purpose was to provide local information for people who maybe somebody was looking for the closest Chick-fil-A or something, that we would have somebody there just to answer questions.
Bruh.
And Gary, did you have anybody answer questions when you were at the table? Ask questions, I mean? I didn't have one question for local information when I was at the table, but we met all kinds of people from the state of Missouri who had no idea that we were around, and we've only been here since 1972. So it was interesting, and it was awesome to meet these people who were all involved in creation ministry, who all wanted to know us. And so, as I said, we met a lot of folks. Here's the other thing we did. We set up a table in a hallway. We had permission of CRS, Joel Brown, the director, who used to come to our meetings, to record podcasts there. So Steve set up in the lobby, or not in the lobby, in a hallway on the side, and we taped 11 podcasts. One of them was only 15 minutes, but most of them were between a half an hour and 45 minutes.
Yeah.
And we interviewed such prominent people as Rob Carter and Spike Piceras, his interview was, Steve and I both did that. He was blowing my mind with some of the stuff he was telling me. Georgia Purdom from Answers in Genesis. Andy McIntosh, who came all the way from across the pond to come over to the conference, changed hand. One of the people that Steve and I interviewed was David Reeves. I don't know if any of you are familiar with him, but he had a TV show that he did for years called The Heavens Declare. And he would interview, prominent PhD scientists on a variety of topics. At any rate, he has an amazing story. And when we play his podcast, how he got involved in this whole thing. He started out as an 8-year-old. He's living in Tennessee, and he's finding fossils in his backyard, realizes that this is evidence of the flood. So from the time he's 8 years old, he kind of built up to the point where he now has a place in Dixon, Tennessee called the Wonder Center. And the Wonder Center is 100,000 square feet.
Wow.
And it's the Creation Museum, but it's not the Creation Museum. Here's why I say that. The Creation Museum follows the creation account through the Bible. What the Wonder Center does is presents scientific things and points to the creator. So it's kind of well, we went down there this weekend, my family did. My grandson and I, and it was an amazing weekend. We visited family down there and we all went to the Wonder Center together. But they have a planetarium there that's one of the 10, considered one of the 10 best in the world. They did a thing that Nikola Tesla, they had the coils, they did all kinds of, they had the stuff that he used, and they played one of who was the Maple Leaf Rag? That was Scott Joplin. They played the Maple Leaf Rag, and these coils were reacting to it. No wires, no nothing, and it was creating lightning in front of the theater. And the lightning, no wires or anything, was lighting up a neon sign on the front. And of course, they pointed straight to a creator. So it was really awesome, and I've got, I'll put these on a table, and anybody who wants to take one, take one. But here's the other thing David did, or does. He's got Genesis Science Network. It's free, 24 hours a day, 7 days a week of creation programming, interviewing PhDs, presenting different scientific things. And I've got a brochure. You can all take one as well. And guys, I'm gonna hold it up here. Steve, tell me when it's on there, right there. So if you want to hit that QR code, those of you who are not here, I'll give you 10 more seconds. So
It looks really good. It covers your face, Mark. That's nice.
there are some that would say, no, I don't think they'd be. So I'll have these on the table. Please take one. But it is, I highly recommend going.
Obviously.
And they have, I mean, there's a place in the basement where they have like artifacts from biblical times. Like they have a shekel and they have a denarii that's in a case down there. And Benjamin was able to find out how to write his name in, what was it, Aramaic?
We don't know what language. We thought it was Hebrew. No. We thought it was Greek. No. We thought it was Aramaic. No. We still don't know.
Whatever it was, I'll have to go back. We have to go back now and see what it was.
Yeah.
So I highly recommend both of these things. It's worth the trip. And for us, we had, my niece moved her family about an hour away from the museum. I guess they've been down there for a year and a half, maybe 2 years. And we got a chance to go down there and spend time with them, and they're believers. They went with us, and it wasn't enough time to see everything in there. So, but I highly recommend it. Finally, out of the CRS conference, we're having some really cool opportunities develop. And it's too early because I don't know if they're going to come to fruition or not, but we'll let you know if they do. But we're going to have some great opportunities, and Steve is working on editing the podcasts. And maybe a couple of weeks we'll have the first one posted. The big problem we're going to have is determining which one to put on first, right?
It's the first one he gets done.
Yeah. So there you have it. Does any of the other board members have anything? Scott, the Zoo Day.
Yeah, so let me do that too. So the Zoo Day indeed is coming up here September 29th and 30th. Signups are going to be going and starting out. In fact, that's already out on the website. If you want to go to our website, you can go to our events calendar and find those dates. and take you to a link where you can sign up for that. But I'm going to have an announcement going out, and then later on this week we're going to have an announcement going out to our MAC email list as far as that goes. And that was one of the things that was really cool, that we did get to connect with all these people from across the country. And they were excited to hear about us, but then as well to hear about the things we were doing. And every time we told them about the zoo, they were just like, why isn't this happening in zoos across the country? And all. And we need to talk, you need to talk to this guy, and you need to talk to this guy. And so we had all these connections in there. That was just really exciting.
That was Eric Hovind.
Yeah.
Who was interested in having us spread the word. We said, hey, whatever we can do, you know.
Yeah.
So
yeah, but it was really good to be able to connect with the different people at the different ministries and that's where I would end up just encouraging you. Anytime there is a creation event coming in town and everything, is to go. And even I think I got more out of the interaction with the people between sessions, more so than I probably would have had in the sessions themselves, just because it was so exciting to hear of what all these other people were doing, and really just how God was moving in so many different ways. So it was just an exciting time, though. It really was. I really came across encouraged.
right, and I did as well. One thing Eric Hovind did, Scott was at the table, and he went up to Scott, and he goes, and Scott was telling him about the zoo day and some of the other stuff. He goes, how come I don't know you guys? He said, I have a website where I list speakers in every state or every city.
Yeah.
And he said, why don't I have all of you guys on there? So we're in the process of getting it on there. So.
Yeah.
All right.
Anyway, but it was good.
All right. So having said that, we will get to our presentation tonight. Mr. Zak Klein is going to present Mount St. Helens, Evidence for Noah's Flood. And so I will introduce our board member and friend and self-professed geology
He's a nerd.
nerd. That's it. I wanted you to say it.
You said self-professed. I wasn't sure.
Zak Klein.
I will have these on the table back here.
Okay, well, good evening. Thank you all. Thank you, Marv. This is a fun presentation for me to give. I've given it before here. In fact, can I get a show of hands? From hearing me talk about it, how about a show of hands for anyone who's heard about Mount St. Helens at all? You're familiar with it? Okay. And keep your hands up if you've heard about it from a creationist perspective in particular. Most of us have, right? Creationists have been talking about Mount St. Helens quite often. Yeah, that's right. Yes, it would have been an action. In fact, I've got a citation of one of those articles. Creationists have done a lot of work at Mount St. Helens. We like to lead field trips out there. I've led some of those field trips. I did get to spend some time out there at the volcano, giving presentations and really getting to spend time in the landscape and learning a lot of things from the local creationist community, as well as other folks that travel out there for research. And so I want to hopefully kind of refresh our memory of the actual eruption. We'll go through some of the key aspects of the 1980 event and some of the things that took place afterwards. But I also want to try to communicate why creationists get so excited about Mount St. Helens. It's one of those things where you could oversimplify the argument. You know, creationists don't believe that Mount St. Helens proves Noah's flood. For one thing, it's not a flood, right? It's a different type of event altogether. And yet there were things that happened at the volcano that got creationists really excited, because they were the same types of processes that creationists have been thinking were probably happening during Noah's flood. And now we get a case study, right? A field study. We can actually see what these formations look like, and we know how they were formed because we were able to observe it. The 1980 eruptions of Mount St. Helens were to date the most scientifically studied and observed volcanic eruption in history. there had never been a volcanic eruption where geologists knew it was coming and had instruments set up and were ready and waiting. Of course, they were completely ready, as it turns out, but they were there. They were paying attention, right? They were taking notes. And that's what made it such an important event in terms of just the history of the science of geology. And for creationists, it gave us a chance to see what geologic catastrophes look like up close and personal. So we got to do a little bit of geology 101 to make sure we're all on the same page here. Most people have a concept of a volcano, which is, it's a mountain that spews lava, ash, and so forth out the top, right? That's basically correct. A volcano really is any place where the molten rock, it's rock, right? The magma under the Earth's crust is able to, or in the Earth's crust, I should say, is able to erupt onto the surface. And it doesn't have to be a mountain. In fact, the biggest volcanoes on Earth don't have a volcanic mountain at all. Does anyone know off the top of their head the biggest volcano in the US? Yes?
Yellowstone?
Yellowstone, that's right, Yellowstone National Park. That's a huge volcano. I don't have the dimensions handy, but it's miles and miles and miles wide. But there's no mountain. Well, that's because Yellowstone is such a violent volcano that if there were a mountain, it would have been blown up when the volcano erupted. We call those supervolcanoes. Mount St. Helens is not a supervolcano, thankfully. We would probably not be having this presentation if it had been. It's a type of volcano that's sometimes called a stratovolcano. That's the term I prefer, but it's also known as a composite volcano. And those are the volcanoes that make these nice cone-shaped peaks that we often imagine, we think of when we hear about a volcano. And the way this works is each eruption, you can see the layers there, hopefully, in that cross-section. Each eruption puts down another layer of lava or ash or pyroclastic debris, different types of material. That's why we call it a composite volcano. It's made of many different types of things. And that builds up this cone. And many, many eruptions will build this cone to be very, very tall and create these very picturesque stratovolcanoes like Mount St. Helens. I'm going to skip through this, this structure of the Earth, but this is part of the engine that drives the volcanoes. And we talked about Mount St. Helens. Mount St. Helens is part of a chain of volcanoes. And by chain, we mean it's a line. There's a line of volcanoes that are all kind of related. They're like cousins. Okay, they have some shared volcanic DNA, you could say. And if we look at these on a map, you can see very clearly all these red triangles. Those are all volcanoes. Mount St. Helens is one of them. It's kind of there in the sort of the center of the photo there of that map is Mount St. Helens, but it's in the same line as Mount Rainier, the tallest mountain in the continental United States. Crater Lake, Mount Shasta, Latin Peak, Mount Adams. All of these volcanoes are related. They're part of the Cascade Range, the Cascade Volcanic Range. And those volcanoes exist on the northwest coast of North America for geologic reasons. There's plate tectonics going on in that location that is driving these volcanoes. They're all fairly young volcanoes. Even in evolutionary timelines, they're only thousands of years old. So it's a fairly young volcanic range. And it has many of the most picturesque mountain peaks in North America. Mount Rainier, as I mentioned, Mount Shasta, Mount Adams, Mount Baker, and Mount St. Helens. Now, Mount St. Helens used to look a little bit different than it does today. This is Mount St. Helens, I believe I think this photo is in the early 70s. This is the way that it looked before it woke up and began rumbling in the late 70s. A very picturesque volcano. One of the most symmetrical in terms of that cone shape we talked about. It was a very aesthetically pleasing, kind of like a Mount Fuji, if you will. If you've seen those, that volcano from Japan. Very picturesque, beautiful landscape. Alpine Lake, Spirit Lake is what we're looking at here, nestled in one of the basins at the foot of the mountain. By the way, that lake there, this is off script, but I think it's fun to point out, that should have been a hint, because that lake only exists because of Mount St. Helens' past volcanic history. We'll maybe talk about that in a moment as we go forward. Well, that beautiful picture, that postcard image of Mount St. Helens began to change. It began to change before the big eruption. This is a photo from spring of 1980, April 1980. And over the months, the mountain was beginning to have earthquakes. It was beginning to put off small amounts of ash and volcanic gas. and geologists knew something was coming, that the volcano is waking up. All of the Cascade volcanoes, or most of them anyways, are active, meaning that there is still molten material underneath them to drive a new eruption. But for the most part, they're dormant. They're not actively spewing anything out. And Mount St. Helens have been dormant for a long time. But in the spring of 1980, earthquakes began to happen, which indicates that magma is beginning to move its way towards the top of the volcano. And we began to have these small eruptions. And geologists, you know, it's like moths to a flame. They all began to swarm around the area to see what's going to happen. You know, maybe that wasn't a good idea. But, you know, it's human curiosity. That's what we're going to do. By late spring, end of April, early May, the mountain began to deform. It began to change its shape. And that hump you can see there in the center center top of the photo, that is not where the volcano used to be. That is material that has been pushed up and outwards because of magma that was pooling. It was accumulating inside the volcano. And this was an indication that Mount St. Helens was, we could say, a very sick volcano. Because instead of the magma just coming up the top and erupting like we expect a volcano to do, the molten rock built up inside the volcano, and for some reason it couldn't get out the top. Something must have collapsed, some of the internal structure of the volcano must have changed, so that the molten rock couldn't escape out the summit and create the crater and the eruption that they would have expected. Instead, it begins to balloon out. It begins to deform the mountain. And geologists had never observed this before, but they knew something dangerous was going to happen. Because that rock there is not stable. All right, you're talking about the entire flank of a mountain being pushed out hundreds and hundreds of feet beyond where the cone is able to support. And so at some point, that's going to go. That was going to give. And so geologists realized that they were looking at the potential for a very large avalanche event. And so they did have restricted zones around the volcano. They cleared people out about 30, 50 miles or so away from the volcano. They had the local communities were evacuated. Even so, none of them were prepared for what was actually going to happen on the morning of May 18th, 1980. I was hoping to play this video, but let's see. I'm going to need you to mute me. Now everyone in the back can probably hear the narration there. So I'm going to play that again. I'm going to try to break down what's going on. We're going to look at this in more detail, but I'm going to try to draw your attention to a few things going on in this animation. This animation was produced by geologists, so actual scientists that studied the eruption, and then with the photographs, they were able to put together this very realistic reconstruction. So let's watch this again. This is the moment before the big eruption happens. At this moment, there is a earthquake. That earthquake is just another one of those earthquakes from the magma moving inside the mountain, but it was enough to trip that big mound of rock that had bulged out from the mountain, and it begins to slide down. We get back to the photo there of the volcano. You're going to see there's a landslide going on the north foot of the mountain. That's what we're looking at here. This is the mountainside rolling off, sloughing off, and then above that you can start to see the explosion. the steam blast. It's not ash at this point, it's mostly steam exploding sideways, laterally out of the north face of the volcano. Now, as this gets very confusing to see, but what's actually happening is that steam blast is going faster than the landslide that released it. So even though the landslide happens first, and this enormous amount of rock is pouring down the mountainside, that steam blast is going much faster and actually overtakes it, speeds past it, and in many locations, it actually strikes the landscape before the avalanche does reach it. So let's break that down again. These are the actual photographs that animation was based on. That big rolling lump there on the foot of the mountain, that's the side of the mountain rolling off. It's actually called a rotational block. It's rolling off the side of the mountain. As it does that, you can see just the beginning of the explosion cloud. There's actually two of them, one in the center and then one towards the top. The darker material at the top, that's mostly rock. It's being pulverized and sent into the sky. The lighter colored cloud is steam. Can anyone guess why we have so much steam coming out of Mount St. Helens when it first erupts? Any guesses?
Snow.
Snow, ice. Pressure is obviously driving all this. That magma is suddenly able to expand. It's been compressed by all that weight of rock. But it's that magma, that molten rock, hot molten rock, interacting with the ice and snow that creates the steam explosion. And that steam explosion is really what dominates this first wave of the blast. It creates what we call the lateral blast. Lateral because it went sideways. That was something that geologists were not ready for. Okay, volcanoes are supposed to erupt in which direction? Up, right? So when you draw your boundary, you make a circle around the mountain. Don't go near the circle. Stuff's going to fall on you. Nobody was expecting Mount St. Helens to just shoot point blank out its north side. And that is a big reason why it was such a devastating eruption and why there were as many casualties as there were, although thankfully there were not as many as could have been. This lateral blast actually behaved more like a fluid than like a dry cloud of dust and ash and so forth. It was the surface temperature was measured to be around 550 degrees Fahrenheit, scorching hot. Any trees that were not blown apart by the blast were just cooked up instantly and were dead. The force of that initial blast was 20 million tons of TNT. I'm not going to use a lot of numbers in this talk because at some point they just kind of melded. But just for context, that's 1,500 times more powerful than the atomic bomb that destroyed the Japanese city of Hiroshima. 1,500 times more powerful in that initial blast. That's not counting the rest of the eruption that followed. Over 150 square miles of the forest was leveled almost instantaneously by this blast. After that steam blast, the mountain began to erupt more conventionally. We call it a Plinian eruption, where we have ash being ejected out the top of the volcano. That ash cloud spread over much of Northwest America. In fact, this map here gives you an idea of where the ash fallout was. It's most heavy, of course, in northeast Washington, much of Oregon, Idaho, and then it went as far as Nebraska and New Mexico and so forth. And ultimately, because some of the ash ended up in the jet stream, bits of Mount St. Helens ash did make it all the way around the world. After a few weeks, it came back to Washington. They actually were able to detect it. So it did make the whole round trip. So he said the forest immediately on the north flank of the mountain, the north side of the mountain, the forest was completely devastated. This is actually a little bit further away. So you see the trees are leveled. It looks like straw, right? Those are trees, and they're not just any little tree. These are big trees. Many of these are old growth trees, 100 feet tall. These are massive trees that were just snapped like toothpicks. And if the trees were unlucky enough to be close to the blast, the tree was just vaporized, and you have a shattered stump. That's all that's left. There wasn't even a log. So incredible power. You got to remember, you have the hot steam blast, but it's also carrying with it rock. It's like a giant sandblaster. And if you're at ground zero, it would simply decimate anything in its path. Another picture. So again, further away from the volcano, the trees are, a few trees are even standing in this photo. It looks like grass. I know it's unfortunate there's no scale here, but those are big trees, completely stripped of their growth, and most of them leveled. Even today, you can still see much of the flattened forest at Mount St. Helens today, 50 years later. So the landslide we discussed already, that's this bulge that's rolling off the mountain here. That landslide, it was overtaken by the blast. That's why we talked about the blast first, because the blast really did reach most locations before the landslide did. It was moving much more quickly. But the landslide was also devastating. The ridges around the north flank, the north side of the mountain in the valley are completely scoured of soil. That would have been a completely forested hill with topsoil, shrubs or ferns, trees, and so forth. It's completely bare rock. And that was the landslide that did that. The landslide would have flowed over this ridge and stripped everything off of it. It actually left the grooves. You can find grooves gouged into the side of the cliff there from this landslide. The landslide also did something else. Remember that lake that I mentioned early on, that beautiful Spirit Lake at the foot of Mount St. Helens? Well, when that landslide plowed into the lake, it created a tsunami. And I've got a simulation here I'm going to play. This is a simulation of a landslide tsunami that happened in Lake Tahoe. So this is not Spirit Lake, but it's the exact same type of phenomenon. So we're going to watch this. We're going to see material is going to fall into Lake Tahoe in this simulation on that far end of the photo, and you're going to see the wave propagate through the lake, and it's going to cause the lake to oscillate, going up and then down and up and down. That's a tsunami. That's what a tsunami is. A tsunami is when you have displacement of the water, it creates a wave, and that wave propagates across the body of water. The tsunami generated at Mount St. Helens in Spirit Lake was over 800 feet high. So an 800-foot high wave of water sloshing up on the ridge lines around Spirit Lake. And you got to remember the sequence of events here, right? What got to the lake first? The steam blast. The steam blast has knocked over all the trees. Then the landslide comes in. It creates a tsunami. The tsunami washes up onto those ridge lines that are covered in trees, and it brings them back down into the lake. And now we have the Spirit Lake log mat. It's over 1 million logs. Initially, many of them have sunk, but over 1 million logs ended up being pulled back into Spirit Lake. In fact, it was so fully covered in logs that when geologists first got back to the area in the days and weeks after the eruption, their first reports back was Spirit Lake is gone. They couldn't see it. It was covered in logs and probably ashfall and other material. Now there's about maybe 400,000 logs left still floating in Spirit Lake. The log mat is very dynamic. It moves with the wind. And so Spirit Lake can look different depending on which way the wind is blowing at a given time. You can actually walk out on the log mat in some places. It is somewhat accessible in the National Monument today. I'm going to skip this next slide.
So they're still floating today?
They're still, oh yes, that photo is only from a few years ago. So yeah, that's 2017. That's my photo when I was out there. Yep, they're still there. I might talk about this more later, but different trees absorb water differently. So certain trees have become waterlogged and sunk, while others remain floating. So there's some species differentiation going on with the log mat. This is not a major part of the talk, but I just do want to acknowledge it, the human impact of the eruption. There are, of course, several famous individuals who were killed. A total of 57 people died at Mount St. Helens, which is tragic. But that number easily could have been in the hundreds. In fact, the fact that the eruption occurred on a Sunday morning meant that a lot of the loggers who were being sent into that forest to harvest trees because their bosses were worried they might lose their tree allotments, those loggers were off for the day, most of them. And had the eruption occurred on a Monday morning, there would have been several hundred logging workers in the area that was devastated by the blast. So 57 people did perish at the volcano. The gentleman on the top left there is named David Johnston. He's a geologist, was a geologist. And he was one of the researchers that was really at the front lines observing the volcano and warning of the dangers. Geologists had a lot of persuading to do because a lot of the locals just didn't really buy that the eruption was going to be that dangerous. It was just very hard to fathom that a catastrophe was really about to occur. And so these geologists weren't just there for spectators. They were trying to, get across the message to the general public. This is really dangerous. You got to pay attention to this. And so David Johnston was one of those scientists at the front line, and he was completely, he actually was the one who gave the radio signal. He was the one who called back and let his team know that the mountain was erupting, and then he was killed very quickly afterwards. The gentleman on the top right there is another famous individual who died at the volcano named Harry Truman. He was one of those stubborn locals that didn't listen to the scientists, and he and his lodge were buried by that landslide. He lived right off the coast of Spirit Lake, and no trace of either of these gentlemen was ever found. So there is a memorial at the monument today. There's a memorial to the 57 people who did die at the volcano. Okay, so now what I want to do is I want to go over this sequence of events. So Mount St. Helens, when it erupted, it didn't just do one thing, right? You hopefully picked up on that by now. It did a bunch of things, right? And they did a bunch of things that all kind of happened at the same time. They interacted and they affected each other. And that's one of the lessons of Mount St. Helens that I like to try to emphasize, is that geologic catastrophes, like a big volcano, they're never simple. They always involve lots of different factors happening all at once that interact in complicated ways. And it could take some work to reconstruct exactly when you come back after the volcano erupts and you try to understand, well, what caused this and what caused that feature, right? It's easy to say, oh, the volcano erupted, but it's not that simple, right? And there's a reason why I'm emphasizing that, and I'll get to it when we get towards the end here. So we have a sequence of events that we've already gone over. The first one is, of course, that landslide, right? That's the big thing that the geologists were worried about, because that bulge was going to happen. They knew there was going to be an avalanche. They knew there was going to be a landslide. And that landslide drastically changed the topography, the landscape around Mount St. Helens. Obviously, that big horseshoe-shaped hole is a pretty big change, right? That is not how the volcano looked before the eruption. Oops, go back there. I'll turn back again. You can see this up in this profile. The mountain from being 9,677 feet tall to being now 8,300. So it lost about 1,300 feet of elevation. And it really lost more than that, because that's just the outer edge. And you got this big old cavern, this big cavity, this horseshoe-shaped crater. It's not just the hole in the top of the volcano. The whole landscape in front of the volcano changed. So the landslide filled in much of the basis of Spirit Lake, forcing the water of Spirit Lake to now rise higher, which became a major problem actually later on. There was a lot of worry about Spirit Lake overtopping and flooding out and potentially destroying outlying communities. We have new lakes that were being formed by the eruption. There were several places where the landslide blocked creeks and rivers and streams, and water filled up behind them and created lakes that never existed before. In some locations, the original ground, the original bedrock of this area that used to be this beautiful forested landscape is buried under 200, 300, 400 feet of new material, new earth. So when we would take people out there on field trips, one of our fun gotcha questions was we take people out to this parking lot out where one of the hiking trails is out there in Mount St. Helens. And we would ask the guests on the field trip, we would say this: if you were standing right here 1 year before the eruption in 1980, what would happen to you? And everyone goes, oh, you get killed by the eruption. No. 1 year before the eruption, what would have happened to you? You would have fallen about 250 feet to your death, because you're standing on ground that didn't exist a year before the eruption. That's how much the landscape has changed, and it changed essentially instantaneously. And that's one of the first points that we like to draw out of this event. It shows us that when landscapes change, they change quickly. That goes against the way that a lot of geologists are trained to think. Geologists are trained to think that a landscape basically doesn't change much at all. It changes slowly from wind, rain, streams, and so forth. And that over a long period of time, you can get dramatic features, canyons, and so forth. What Mount St. Helens showed us, though, is that when the earth changes, it actually changes very, very quickly. And then after the big change, the wind and the rain and the streams and so forth, they do modify that landscape, but they don't produce the landscape. They are simply tweaking. They're kind of coloring in around the edges of a landscape that came to be in a very short amount of time. Now, after the big eruption on May 18th, 1980, Mount St. Helens continued to erupt for several months and years afterwards. the next big eruption occurred in the summer of 1980, in June. This eruption was not as dramatic as the big one in May 18th, but it was a very important eruption. It produced a type of volcanic process that is called a pyroclastic flow. And we have a picture of this. It gives you a sense of what this looks like. A pyroclastic flow happens, well, one way it can happen is when a volcano erupts, it sends material up into the air, and then at some point, some of that material gets lofted away in the wind, but some of it comes back down under the force of gravity. It falls back into the volcano, okay? When it falls back into the volcano, normally, if this was a healthy volcano, just with a nice crater at the top, right, it would just kind of keep going up and down maybe for a while. But Mount St Helens has this big hole in its front lip, right? So when that material falls down, it doesn't go back up. What does it do? It shoots back down out of that open horseshoe-shaped crater that's funneling the material down into the valley to the north. And that's what creates these pyroclastic flows. The material is being ejected up, it's coming down, and then it's coming down the flank of the mountain in a roiling cloud of essentially pulverized rock. These pyroclastic flows are deadly. I'm going to play a clip here of one. They are actually the thing that kills most geologists who work at volcanoes. Everyone thinks that volcanoes are dangerous because of lava. You can walk faster than lava goes in most cases. If you get killed by lava, you were being kind of stupid because you can get away if you see it coming. But pyroclastic flows aren't that way. These things are unpredictable. They don't behave like a normal landslide of this material going downhill. They can go uphill, they can go around obstacles. They can behave very, very strangely, as you're going to see in this clip, which is from a volcano in the Philippines. So this is a pyroclastic flow. Again, the idea is the material is coming down, and there's a valley, probably a river valley in this case, that's channeling the material down and allowing it to form this roiling cloud of gas and rock debris. And you can see it behaves almost like a fluid. Not exactly. It's very hard to describe. I am told that this gentleman and this vehicle did make it away safely. The flow is not going to actually reach the camera, at least not in this clip. So, but you can see how it behaves, right? It does not care about topography. It's going to get you if it wants to get you. And these things are incredibly dangerous. And if you get caught in one, there's no surviving. They pretty much vaporize and pulverize anything in their way. And at this point, it looks like it's run out of steam and it's beginning to waft away in the wind. So fortunately for this film crew, this flow did not continue down the street. But you can see these things are incredibly dangerous. And they're also incredibly interesting. Kind of odd how that works in geology. The dangerous things are very interesting. Because what this pyroclastic flow at Mount St Helens created, it created a deposit. Now, it's a little hard to make out in this photo, so I'm going to outline it for you. The canyon we'll talk about in a minute. But for now, ignore the canyon and just enjoy that we have a nice cross-section. This cross-section allows us to see deposits that were produced at the bottom there on May 18th, 1980. That's called ashfall tephra, just ash that fell out of the sky. A pretty thick layer of ash. Then there's that middle section that we're going to talk about. That is the pyroclastic flow deposit. And you might be able to tell from this picture, but we'll zoom in here in a minute. But it's not just a random homogenized mess of bits and pieces of rock like you might expect. It's actually very finely laminated or layered. And if we zoom in here, we can see what I'm talking about. These layers, now I want to be clear, this is not rock layers, because these things aren't rock. You could dust them away in your finger. They potentially could become rock with time. But right now, they're still mostly soft material. But you can see it creates these very fine, we call planar lamination. That means it's flat line. And there's different ways that layers can be arranged. They can be tilted and so forth. They can be curved. In this case, they're planar. They're like a flat plane. And these planar laminations are really interesting because they resemble the kinds of laminations, the kinds of layers that we find in many sedimentary rock formations. This is a photo I didn't take, but my brother took it. But we're hiking out there together in the that valley to the north of the mountain, and you can still see these laminations. In some places, the weathering has kind of obscured them, but we found a place where there had been a little bit of excavation. This is not a very big clip, by the way. This is that's probably like 3 feet or so of exposure right there. You can still see these very thin, flat-lying laminations. Oops. That's another image. This is my wife and I in 2014 in the valley looking at some of these laminations. Very, very interesting. We'll talk more about the significance of those in a minute. But briefly, I think you might be able to appreciate this. Those look like laminations that we find in the rock record, right? Laminations that most geologists would tend to think form through every year a cycle of winter deposition and spring runoff, and you produce a little thin layer of material at the bottom of a lake, perhaps. And yet, these pyroclastic flows were able to generate that stack of layers. I forget the exact thickness there, but that's at least 15, 20 feet right there in a matter of hours, very, very quickly. Each of those individual layers probably took a matter of seconds to form. Okay, so that was summer of 1980. Now we're going to zoom ahead. We're now in the spring of 1982. It's been a few years. Mount St. Helens has finally quieted down a little bit. And you can see it's white. It's covered in snow. In fact, ice began to build up back in the crater again. So it seemed like maybe Mount St. Helens was finally ready to cool off and chill off a little bit. And then it erupted again. Now, it was kind of a puny eruption. I mean, look at that cloud. That's not really impressive. But it was enough to make that crater hot. And if you have a crater that's full of ice and it gets hot, what's going to happen?
Water.
It's going to get full of water. And that water is going to get mixed up with what? Ash. Yeah, dirt, but ash in particular. All that pulverized rock that's still filling the crater. And when water and ash get together, it produces something that geologists like to call mud. It's unlike most kinds of mud, though. In particular, especially on a volcano, it tends to be very hot. Also, just look how black that stuff is. It's pulverized rock mixed with the water. And these mud flows, now this picture, it might look a little bit lazy. I mean, it's just sitting there. This is after the mud flow is mostly completed. But let me show you what these mud flows actually look like when they're happening. This is another, I believe this is also from the Philippines. A lot of good volcanoes in the Philippines. This is a volcanic lahar, a mud flow produced by a volcano. It's called a lahar. And these things are incredibly destructive. You have to remember, they're not just water. It's like a liquid sandblaster. If the steam blast on May 18th was like an actual sandblaster, this is like the liquid equivalent of a sandblaster. They are so full of sharp rock fragments that they can cut and carve their way into material very, very quickly. They're also highly dense. They're denser than water. See that boulder there? That boulder is floating. Okay, boulders don't float in water, but in lahars, they float and they move quickly. These lahars, these mud flows, can destroy bridges. They did destroy bridges. They can do immense damage to infrastructure. They can also do a lot of damage to the surface of the earth, such as this. This is the canyon that was excavated by that mud flow in March of 1982. And we're going to get some pictures with people in them, so you'll see some scale here. There's a little creek there at the bottom. We'll talk about that in a minute. Here's a picture of more recently. This is a picture that I took in 2014 when I was able to go down into that canyon. And that cliff right there, that's one of the deepest points in the canyon, is around 200 feet tall. And this canyon was cut in a matter of hours in March of 1982. An incredible drainage canyon. And the reason why that canyon was cut there, you see there's a stream running through it now. We're all kind of relaxing, and we've been hiking for a long time in that photo. And it was nice to get to just sit by the water and cool off a little bit. Some of us were a little more adventurous and decided to try to scale the wall with mixed success. It's pretty steep, and the material is still fairly loose, and so it's hard to get good footing. But notice that creek running through the canyon. Yeah. Okay. Now, when geologists see a canyon and they see a creek running through it, what is the first thing that tends to come to their mind? The creek made the canyon, right? And it's understandable that they would think that, okay? Because creeks do erode, they do cut into their banks. They can do some erosion, they can do some impressive erosion if they have the right steepness, the right gradient. But something to keep in mind, where do creeks go? Where do streams go? Downhill. They're going to go to the lowest point. And if a canyon is available, where is the river going to go? It's going to go through the canyon, right? Before this canyon was cut, where did that river go? There was no river. In fact, that was one of the problems. After the May 18th eruption, geologists were looking around at the new landscape they were left with and realized there's nowhere for the water to go. we got a problem because all the normal drainage systems that used to come off the flank of the mountain to the north were all buried by that landslide. And until that canyon was cut in 1982, there was no Toutle River. This is called the Toutle River. There was no river there. There was nowhere for it to flow. It only began flowing again after that canyon was cut. So it's a way that the Mount St. Helens kind of subverts our expectations a little bit. It shows us that just because we have this phenomenon of a drainage canyon with a drainage in it, it doesn't mean that the river cut the canyon. In this case, we know it didn't because we observed it. Yes?
What's the source of the water? Where does the water come
Off
from?
of Mount St. Helens. So snow melt every year.
Snow melt,
Yep,
snow melt,
springs.
okay.
Yep. The water's still building up inside the volcano. It has to get down there somehow, and it's got to make its way down to the Columbia River. Ultimately, is the main drainage in that part of the world. I was going to say. Oh, go ahead. Yes.
So in a cold winter, does it dry up?
Does the stream dry up?
Yeah.
Not entirely. There are places where it does. There are washes that are kind of ephemeral and they don't flow all the time. But there is a North Fork of the Toutle River today that is pretty consistent. It don't get much deeper in the spring, but there's pretty much always water down there. Where was I going to go with that? I had one more thing I wanted to say and I lost it. So I'm just going to keep moving. Maybe it'll come back to me later. This is what the canyon looks like from Johnston Ridge, which is the northern viewpoint of the volcano. You can see this really beautiful and dramatic branching canyon structure running across the valley. And that arrow there is pointing to one of the cliffs. That particular cliff is around 100, 140 feet high. There are places that are a bit deeper than that. A very dramatic and a very spectacular canyon. That's what I was going to say. So this concept that streams cut canyons is so ingrained into geologists and just even the general public that I have been at Mount St. Helens and overheard rangers telling people who ask about that canyon, you can see it from the visitor center. And when they ask about it, they'll say, oh yeah, the Toutle River has been, ever since the eruption, it's been carving and cutting that canyon. Now they don't know any better, okay? No one told them to say that. Geologists know that's not what happened. And they're just going off of common experience. They've always been told that rivers cut canyons. There's a river, there's a canyon. Seems pretty simple, right? And we don't correct the rangers that this is, that their turf, their territory, and they're not being malicious. They're just, that's just kind of common sense, right? You see a stream running through a drainage canyon, and you assume that the stream is the cause of the drainage canyon. And yet we know, because we observed it, we have satellite imagery and photographs before and after. We know exactly when that canyon was formed.
So can you ask them? Can you say, sir, I'm from St. Louis.
Yeah.
Mississippi River goes right through.
We'll talk about that maybe during Q&A. Generally speaking, I try to pick fights with rangers. Okay, they got a hard job. They're only given so much information. They're not experts. And they're not going to take lessons from every visitor because if they did, they get told a lot of things, right? Lots of folks come through. So yeah, if I have an opportunity to spend some time with one, maybe I'll talk about it in that context. But you don't want to embarrass them, right? They're just giving. They've been trained to say some things, and that's then they're going to go back to school in Ohio and never come back to the mountain again. All right, the log map. We're almost done with the overview here. The log map, we already talked about the number of logs, over 1 million logs that were washed into Spirit Lake. Those logs, it turns out, began to behave kind of funny in the years after the eruption. They began to sink, but some of them began to sink in a curious way. What do you notice about those logs? They're floating upright. Okay, now that actually makes sense if you think about it, because logs, different kinds of wood in different parts of the tree. And it's not surprising that the root end of the tree might absorb more water, become heavier. And these logs begin to float upright as they sink. And it can take them weeks, months, years to fully sink. But as they do sink, this image was put together by Dr. Steve Austin. If they sink in that vertical orientation, they can actually become buried at the bottom of the lake in a vertical, or we sometimes say a growth orientation. They're buried as though they grew there. You could say they were transplanted there at the bottom of the lake. Obviously, they didn't grow there, but that is where they're buried. And in many cases, they're buried in these upright positions. And I don't have photographs of this, but this has been confirmed by scuba diving work that there are indeed vertical buried logs at the bottom of Spirit Lake. In fact, if you were to drain the lake today, it would probably look like an old forest from all the trees that have settled. Not all of them are vertical, but many of them are. Some will be prone, will topple over. And this is significant because there are deposits around the world with vertical oriented trees in growth position. One famous one is at Yellowstone National Park. I mentioned Yellowstone already. This is a location called Specimen Ridge where there are trees that are buried in lahar sediments, volcanic mudflow sediments, in upright position. And there are many horizons, many layers with trees buried upright at this location in Yellowstone. And the conventional interpretation of this for a long time was that this represents dozens of successive forests over thousands to millions of years that grew, died, were buried, replaced by new forests. But because of Mount St. Helens and because of the observation of the vertical logs in Spirit Lake, even secular geologists have actually changed their thinking at Yellowstone. Because what they realized is that these trees, as I mentioned, they're buried in volcanic deposits. They're not buried in, forest soil. They're buried in mud flows. Not only that, but the trees aren't always buried with other trees of the same species. You've got species from alpine environments and trees that should be at lower levels, and they're buried in the same level at Specimen Ridge. Also, the trees here at Specimen Ridge generally do not have roots. The trees at Mount St. Helens don't have roots either. Why don't they have roots? They didn't grow there, right? They broke off. They've been transported. So even in conventional secular geologic circles, it's generally agreed that these trees were probably transported after a volcanic eruption. And they were buried here at Yellowstone, not in growth location, but in growth position. They look like they grew there, but in reality, they did not grow there. They were transplanted. Last point that we like to draw out here is the way that life responds to this devastation from the 1980 eruption. Immediately after the 1980 eruption, geologists would often describe the area as a moonscape, meaning there was nothing living left in that area to the north of the mountain. Everything was just completely sterilized. That was the fear. In fact, ecologists and biologists were concerned that the native forest might never be able to come back to the area. It was so completely devastated. This is what it looks like in 2018 when I was there. I've been there more recently, and it keeps getting greener every time you go. It keeps getting greener. It's getting hard to see some of the geology, actually. There's so many trees and ferns and wildflowers. It's, in fact, there is a greater diversity of plants and animals in the eruption zone today than there were before the eruption. So far from sterilizing the area, there actually is more life in the blast zone than there was beforehand. And this really baffled a lot of scientists. It turns out that there are certain plants and animals that seem to be specially designed to gravitate towards disaster zones like Mount St. Helens and make it habitable again. And I'm just going to give you two examples. One are these beautiful purple flowers. These are called the prairie lupin. These flowers are of a type of plant. They're in the legume family. And they're a type of plant that is able to take nitrogen from the atmosphere, from the air, and fix it. They actually bring it into the ground. They're called nitrogen-fixing plants. And I'm not going to go into the whole process, but it involves bacteria that live on the roots of these plants. And they are actually able to convert the nitrogen, which is a gas in the atmosphere, into nitrates in the soil, which is a fertilizer. So these flowers actually fertilize their own soil. And when they grow and they create these big purple blooms, this is pumice, by the way. This is like the most nutrient-free type of soil you can imagine. There's nothing here. It's just bare rock. There's no nutrients in here for plants or animals. But these plants are bringing that nitrogen they're creating a soil. They're bringing that nitrogen into the surface and actually making it habitable for other plants. There's more than just the lupin. The red alder tree is another one of these nitrogen-fixing plants that fertilizes the ground for itself, but also for other plants that come in around it. And there's an idea, a theory in ecology about how forests grow. It's called forest succession. And it's simple to understand. It's just the idea that a forest grows in stages, right? You get kind of, shrubs and very plants that grow close to the surface that can deal with sunlight. and you start to get taller shrubs and bushes and trees. And as the trees grow, they start to shade the area, and it kind of changes the balance of what plants can grow there. And this is called forest succession. It's supposed to take centuries and thousands of years to get back to a conifer forest with pine trees, right? That would have been what you would see at Mount St Helens. And we already got the coniferous forest back at Mount St Helens, centuries ahead of time. One scientist said that Mount St Helens just did not read our books, apparently, on forest succession, because what they discovered is that forest succession is true, but in reality, life is just more dynamic, and these things are actually happening simultaneously. And rather than it being long, drawn-out periods and phases, we've got the alder and the lupin and the conifers and a whole variety of plants, the ferns and so forth, all growing together and providing for each other in different ways. And it's incredibly fascinating. And it's not just the plants, living organisms, animals also have responded in very surprising ways. What they discovered is that many of the mammals, such as the elk population at Mount St Helens, reproduce more quickly in a devastated region, which is very counterintuitive, right? The assumption was that they would have fewer offspring, there's less food available. But it actually doesn't work that way. They actually overpopulated temporarily. And this then brought in predators, and it brought in other organisms, and the food chain begins to be restored again. And so it seems that biological organisms are able to recognize we are in a part of the world that needs help. And we're going to behave differently in our breeding habits and our mating habits and our diets and so forth to bring life back into this area way in advance of what scientists expected. I'm going to play this clip. Now, this is from satellite imagery. The red here, red is actually green. Annoying. It's going to change. It's just that the satellite technology changed over the years. But this is going to be a time lapse of the forest being destroyed by the volcano, and then you're going to see how it comes back over the course of I think it's about a minute-long clip here. So we're going to play this now. So you're going to see this is all red. This is green. Okay. There's the eruption, blows out the forest, and now watch how quickly we're going to see the green start to invade. And that devastated wasteland begins to shrink and shrink. It's all right, 1990, only 10 years. Watch that timestamp there. 99, we're at 2000. It's still becoming greener. Spirit Lake, notice how it keeps changing shape. That's the log mat. Okay, the lake is fine. It's just the logs moving around. 2009, 10. I think this goes to 2011. Looks like it stops there. It's greener than that now by far, by the way. In fact, if anything, I think the regrowth is kind of exponential. It accelerates. And it really is the point now where there are geologic features you can't see anymore. And for me, it's kind of frustrating because things I used to be able to point to people and say, hey, look at that cool, it's covered in plants now, thanks. Isn't that something though? And this has relevance to us as creationists who believe in Noah's flood, because Noah's flood would have also been an ecological disaster, right? It would have left a global wasteland in many ways. And one of the challenges that creationists have faced is, can the earth actually come back from that kind of a disaster with just a small population of animals and whatever plants and critters that manage to survive, insects and whatever outside the ark? Well, Mount St. Helens isn't the global flood, but what it gives us a microcosm of the way that biological organisms and the way that ecologies respond to a disaster. They seem like they're designed to fix this problem. They seem like they're designed to behave differently in these devastated regions and in disaster zones like this, specifically to bring life and habitability back into a devastated landscape. There is an idea in geology. Every geology student learns this in Geology 101, and it's called uniformitarianism. We sometimes say the present is key to the past. This has been a guiding principle in geology for centuries now. It's a fairly new idea, actually. It comes out in the 1800s, or late 1700s, rather. And this concept, this idea, it really tells geologists how they're supposed to think about how the Earth changes. And I mentioned this before. they're taught to believe that the Earth changes slowly through the kinds of processes that are happening day in, day out, season by season, winter, spring, ice thawing, rain falling, wind blowing, and with enough time, those slow processes can do incredible amounts of work. That's the mindset that they're trained to have, okay? The counterpoint to this idea is called catastrophism. This is actually the definition I got from the Oxford Dictionary. Catastrophism is the theory that changes in the Earth's crust, that's changes in the surface, during geological history have resulted chiefly from sudden, violent, and unusual events. Now, catastrophism, historically, catastrophism is kind of a minefield, okay? Lots of weird people have taught catastrophism. So I don't want to make it oversimplify it and say that we're all catastrophists. It's not quite that simple. But the biblical account of the flood is a catastrophist account, right? It's an account that says that the earth changed dramatically, very quickly, in a very unusual way, we could say, right? Global floods don't happen every day. They don't happen every century. In fact, they don't ever happen again, right? We have the Rainbow Promise. So you can't get more unusual than that, all right? So as a result, it can be hard for geologists to think, how do you reason about something that only ever happens once, right? What's one of the things in the scientific method we want to be able to repeat, right? Repeat our experiments. You're not going to repeat the global flood. So it's actually kind of hard to think about as a geologist. How do you imagine, how do you conceive of an event that only ever happens once? And so catastrophism gives us some tools, because we can look at smaller catastrophes like Mount St. Helens, and we can glean insight into how the earth works in these devastating high energy type of situations like a volcanic eruption. And I must point out, Mount St. Helens was a puny volcano. This diagram here shows the ash fallout extent from volcanoes in North America. These are all volcanoes that most creationists would agree happened after Noah's flood. And you'll notice that the red one there is the smallest, that little kidney bean. That's Mount St. Helens. All right, that's the extent of the thick ash fall. And look at all the eruptions that happened previously. The yellow circle there, that's Crater Lake, Mazama. The purple and green, those are Yellowstone volcano eruptions. And that's just the extent. This next image, this is the volume of ash that was put out by those same eruptions. So purple and green, that's Yellowstone. Actually, orange is Yellowstone as well. Yellow is Crater Lake. And if you can see it, that red pinprick is Mount St. Helens. Okay? So everything I told you about how devastating this eruption was, scratch that. It is a burp when it comes to the kinds of eruptions that have happened just in North America. There's a much bigger eruptions around the world. And one of the things about these eruptions is I have them here in order of volume, how much ash is put out. You know what other order is? Time. The biggest eruption is the earliest one. Mount St. Helens is the latest one in that sequence. Interesting. Notice that pattern. We have a name for that in science. That's an exponential decline. That's exponential decay, where each one is a significant ratio smaller than the preceding one, and it just gets smaller and smaller and smaller and smaller. This is, by the way, a little side note. When people talk about the Yellowstone volcano, we're overdue for an eruption. This is why they're saying that. They are looking at this, stretching it out over millions of years and saying, we've not had one of these big boxes in a long time. Okay? So the thinking is, well, must be due for another one. But if you put these in a biblical timeline, all these volcanic eruptions, these huge ones, would have happened right after Noah's flood. And they've been getting smaller and smaller ever since. This is not a record of periodic mega eruptions every few million years. This is a big spurt of large eruptions that very, very quickly lost power and became smaller and smaller until now we have Mount St. Helens putting out just a pinprick by comparison. So it really changes your perspective when you look at these things within a biblical time frame. And some of the alarmist rhetoric that goes around there isn't actually as compelling when you look at it as a decline in volcanic power and not simply a repeating cycle. Remember, uniformitarianism, they believe the present is the key to the past. They believe that if a big eruption happened in the past, it's got to happen again today and in the future. It's got to be regular. But when we look at the actual data, we don't see regularity. We see a peak of extreme catastrophism becoming less and less and less and less over time, which actually fits very well with the biblical model. I'm almost done, and then we'll get to questions. Now, that exponential decline doesn't just work with volcanoes in history. It works for an individual volcano as well. When we look at Mount St. Helens, the biggest energy output is May 18th, 1980. That steam blast, right? Leveling the forest. Then we have subsequent eruptions that are still impressive, but much less powerful. And then we begin to have puny eruptions that can produce a mud flow, but not a whole lot of ash. And we have these drainages being carved. And then we have the most recent eruption here is in 2004, just a little puff of ash and gas. And we see an exponential decline of geologic energy being put out over the course of this single eruptive cycle, the single event at Mount St. Helens. And the reason why I bring this up is because this has implications for how we think of Noah's flood. Okay? When secular geologists will say, there's no evidence for Noah's flood, what do they mean by that? They usually mean, I can't go anywhere in the world and see one layer of mud all over the world that I can say, yeah, that's Noah's flood. That's the flood layer right there, all over the world. That's the flood layer, right? And what I want to argue is that that's a very naive and simplistic way to look at a geologic catastrophe, right? Where's the Mount St. Helens layer? It's not one layer. It's a whole complex of things, right? It's many layers and canyons and explosion pits and a crater and landslide deposits. It's a complicated series of events that creates a very complicated landscape. And so when people say there's no evidence for the flood, they're saying, I don't see a flood layer. Well, I'm going to suggest you're thinking too small about the flood. When we look at geologic catastrophes, we see that they are complexes. They have a number of events that begin with extreme levels of energy and then exponentially decline after the big output, after the big event. And I think Noah's flood was very much like this. I think that explains a lot of the complexity that we see in the geologic record, in the rock layers that most creationists believe are from the flood. We don't just see a flood layer. We see dozens, hundreds, thousands of different kinds of deposits that represent different types of events happening within this global catastrophe that we call Noah's flood. Earthquakes, volcanic eruptions, meteor impacts, landslides, mud flows, you name it, it was probably happening during Noah's flood. And so we have to be thinking bigger and thinking in more sophisticated ways. When we talk about evidence for the flood, it's not going to just be, the rains came down and the floods came up. That's not the story, folks. That's not the story. All right, this is a geologic catastrophe, and that means it's going to be a complex of catastrophes. So my premise here, my conclusion is that Mount St. Helens demonstrates that catastrophic processes reshape the Earth quickly. I think we've seen that. I think that's very evident. And that many of these features, both at the big eruption and in the months and years after the eruption, they give us useful analogies, examples, microcosms of the types of features that would have been produced during Noah's flood as well as afterwards. And I'll conclude now with one of my favorite passages. We're talking about volcanoes. Psalm 46, verse 8. Come, behold the works of Yahweh, the Lord, who has appointed desolations in the earth. God allows his power to be shown through events like these eruptions. And through those expressions of power, we get to see glimpses of what God is like, right? We get to see his design, his care, his provision to create organisms and to create systems within the biosphere that are able to bring life back to a barren, devastated landscape. And we also see reminders of the type of catastrophism, the type of devastation that was brought about on the earth during Noah's flood as a result of sin. These disasters happen. They're a reminder that the earth has fallen, that the earth has been affected by our sin. Okay? And so these things are part of the works of the Lord that we are supposed to be looking at, marveling at, and we should be interpreting them in light of what God has revealed in Scripture. And with that, I'm done.
All right.
catastrophe is a word my wife uses a lot.
Different context, Marv.
Oh,
I'm pretty
okay.
sure.
All right, before we get to questions, I just want to say in 1977, I think, my brother was hired as a hydrologist for the state of Washington.
Mm.
And while all this was coming to a head, he actually flew over Mount Helens in a helicopter and was taking pictures and things because he had to estimate what those flows were going to do to the lakes and and he went to he had to go to the governor because he went to the power companies and told them how much they had to lower their reservoir, and they told him to pound sand. So he had to go to the governor and have the governor go to the power companies and say, you're going to do what he says. Wow. So it's was very interesting. So questions for Zach?
You, sir.
Yeah, the one slide they had all the different cubic ashes. I get how you can measure Mount St Helens, but how do you measure the ones that maybe nobody was there for?
Yeah. So ash, volcanic ash doesn't last that long, but when it decomposes, it does turn into a recognizable sediment. It actually tends to turn into clay. And so they can find a lot of these deposits firsthand, like in the field. They can also estimate based on how much that material tends to erode over the years. They can estimate how much used to be there. So there's somewhat educated guesses, but we find ash deposits in those areas that are mapped here. That's why they know they got that far. Then they can base, okay, it's this thick here, it's that thick there. You can do some math and extrapolate. It was probably about this thick over that whole area. So it's pretty, I mean, I'm sure those numbers have been revised. And these aren't even the biggest eruptions. These are just the ones in North America that are used in this particular diagram. But yeah, it's impressive. But first, you, sir. And Gary.
Yeah, like with the ranger, is it ever okay to go to him and say, well, you know, I live in St. Louis.
Yeah.
And the biggest river in North America, the Mississippi River, runs right past downtown.
Mm-hmm.
And when it gets down to the normal boat thing, it's, I don't know, it's 10 foot deep or whatever, 20 right off the arch. And why is it deeper in it's mud bottom, it's not rock like all these canyons like the Grand Canyon? Why do we have a much deeper?
Yeah.
Now I've read a creationist explanation of that, and I accept that, but it's kind of like, is that a good thing to go at?
It would be a good topic of conversation. You know, like I said, rangers are not experts. You know, their main job is to control people and keep people safe. And the educational stuff is something that they do in addition to that, of service. And so, you know, even if they're wrong, it's not usually their fault, right? They don't know the area in many cases. They're brought in, they're given them material to present. So I would bring it up in a non-confrontational way. I wouldn't, you know, as a good faith conversation. I wouldn't try to trap them over it though. And when it comes to the whole river question, so typically how they would explain that is they would say for a river to cut a canyon, it's got to have a certain gradient, a certain steepness where it can actually be down cutting, right? The problem is that when you look at a place, you know, like Mount St. Helens, and actually this applies to the Grand Canyon as well, which I didn't get to talk about, but I have a picture of it here. When you talk about these canyons are cutting across flat surfaces, right? They're not going, it's one thing to say, okay, a river cascading down a mountain slope, you could cut some pretty deep canyons. This Colorado River is not flowing over a mountain, it's flowing over a plateau. You know, that's not a steep gradient to do canyon cuttings. And it's the same thing in Mount St. Helens. That's a flat plain. The only way to get a canyon there is to overtop the plain. It's to actually have so much liquid coming down that it can flow over the top of the plateau and then begin to cut down into it. And that's what happened at Mount St. Helens. And we think that's probably what happened at Grand Canyon as well. So, you know, they would have an answer for you as far as the Missouri and Mississippi rivers, because they don't expect a canyon to be cut in a plain, in a low-lying valley with a very shallow slope, very shallow gradient. They would say, no, you're going to cut your canyons in mountainous regions with steep running slopes. But Grand Canyon and Mount St. Helens, they show that with the right conditions, you can cut a canyon very quickly, even across very flatline ground. Gary.
How many acres does the Mount St Helens area be comprised of? And I presume 45 years ago, there was no cell phone service.
That's right.
In the park.
That's a safe
now,
bet.
Presently, is it an active park experience today?
Yep.
And are there people
Trying to find a picture that shows the monument. Yeah, it's just a very. I don't have a good map of the monument here at the moment. So it's not a national park; it's a national monument, and that's because it's preserved specifically for scientific research. That means it is not as accessible as, say, Yellowstone. There are fewer trails. There's no campgrounds for the most part. It's not very well developed. There's some good visitor centers, 2 of them. Well, one is really good and one that's smaller. I don't know the acreage for you. Sorry, I can't give you that number off the top of my head. But you can definitely go there and see a lot of the stuff firsthand. There's some good trail networks where you, and even just from the visitor center without hiking, you can walk up the edge and see the volcano front and center. It's a beautiful area to visit. Cell phone service depends on your provider, but it's not great.
Can you hear me?
Yeah, exactly. There is Wi-Fi in the visitor center though, at Johnston Ridge. In fact, Johnston Ridge, I don't have any photos of this really. This photo here is kind of taken from Johnston Ridge. Johnston Ridge is actually a little bit further this way. Johnston Ridge is named after David Johnston, the geologist I mentioned, who was killed. It's actually a volcano shelter. And you can tell when you see it, it is built into the ridge. It's got sloped concrete faces to it, and it's designed to withstand another blast, which is ironic because it's not going to ever blast again, right? If you think about the conditions that led to that big blast, it's because the magma trapped under the volcano that couldn't get out. I mean, that's a pressure cooker with no lid. That thing's never going to have another blast like it did in 1980. Even though it could certainly erupt and will erupt again and have flood flows and such. But it's probably not going to be a big eruption. The volcanoes to be worried about are Mount Rainier, Mount Hood, all the other Cascade volcanoes that have not blown their top yet.
Anyone else?
Yes, sir.
Does anybody talk about how much coal is made from the granary?
So there's probably no coal that's been made yet. No coal has been observed yet. Now, what you might be getting at, and it is a good point that I skipped for sake of time, is that at the bottom of Spirit Lake, where all these logs are beginning to sink and settle out, there is a thick layer of something called peat, which is essentially decaying tree bark for the most part. Geologists think that peat is the precursor to coal. The coal seams are formed from peat. Now, that's been done in a laboratory setting. But in order to produce the coal, you have to bury that peat under a lot of other material and put it under a lot of pressure. And that's not happening in Spirit Lake because you just have water, right? It's not getting buried deeply enough to produce the pressures that we think are required to make coal. So it does give us a hint into how coal could form, because if you notice these trees, they're all missing their bark. That's because as the trees float, they actually rub against each other and they rub their bark off each other. And that bark settles out at the bottom, producing the material that in the right conditions could probably become coal. But it's not likely to become coal at Mount St. Helens because there's not enough sedimentation happening. We're not building up enough material at the bottom of the lake quickly enough to bury it deeply to produce the right pressure for coal. So it's likely a first step towards coal. But no actual coal is being observed at this point.
How about one more question?
We got Steve.
Just curious, last time I was there is a bulge that is growing in the middle of the large horseshoe.
Yep.
And any thoughts on what's going on there and what's
so that bulge is called a lava dome. And I was trying to see if I probably have a photo of it. Well, can't see it, but I can point you to where. Oh no, this is a good photo of it. Okay, so if you look there in the dead center of that horseshoe-shaped crater, you should see a bulge kind of towards the upper southern slope. Can everyone see that? That's called a lava dome. That is essentially the new peak of the volcano. If it produced enough lava over time, it would fill in the crater and begin to build the cone again. Now, as I said, I don't think it's likely to do that because it just isn't erupting often enough or fast enough to really get going, and material erodes as well. But that's those lava domes are they blow up. In fact, Mount St Helens has had several lava domes built in the craters since 1980 that have built up and then blown up and then built up and blown up again. It's different from the bulge in 1980 in that it's actual lava that's being piled up, whereas the bulge in 1980 was the old flank of the mountain being pushed out by magma underneath it. In this case, the magma is getting out like a healthy volcano. It is erupting and producing this pile of lava in the center of the crater, and that begins to build over time. And if the volcano erupts enough, it could potentially begin to build its peak again and begin to rebuild its summit. As it is, it would probably take several centuries without it completely blowing up, because every time it blows up, it resets to zero and has to start over. So it has to be just the right kind of eruption to keep building the pile higher, but not destroy it. So that the lava dome is really the area that is still the active part of the volcano. It still gives off volcanic gases regularly, even today, because it is an active volcano. There is magma down there, and every once in a while, enough of it makes its way to the top to create some lava and continue to build up that lava dome.
Okay. Quickly.
One more.
Yeah. You brought up Grand Canyon.
Yes.
A lot of secular scientists are coming to believe that this was not formed by a gradual process, but more catastrophic. Just comments.
Absolutely. Yep. I skipped that for sake of time, but I'm happy to talk about it. The Grand Canyon, as I mentioned earlier, one of the reasons why it's such a geologic mystery is that it's a canyon cut into a plateau. All right. That means that the canyon, before it was cut, was higher than the Colorado River that supposedly cut it. Can you see the problem? All right, water is here, top of the plateau is there. The water has to go over the plateau to cut the canyon. How does that happen? Okay, the Colorado River, rivers cannot run uphill. All right, they cannot run up onto a plateau to begin to cut down into it. The only way to down cut a canyon into a plateau is to have enough water that it can overflow the top of the plateau. And once it does that, it's going to create that steep gradient we talked about, where it's going to start down cutting very quickly. When it crosses the plateau, it pours off the other side, you get sort of like a back cutting waterfall. It's like Niagara Falls, but a lot faster. And it just begins to erode backwards and back cut this drainage canyon. And even in secular geologic circles, one idea that's really catching on is that Grand Canyon was cut very quickly in a matter of decades, maybe centuries, but quite likely even less, by the overspilling of a large lake. There's lake sediments upstream of the Grand Canyon. This area called the Hopi Buttes is a great example of that. The lake is called Hopi Lake. And the current thinking is that lake overflowed the top of the Colorado Plateau, and that's what cut the canyon. And it's actually a beautiful analogy, or I should say the way around. Mount St. Helens is a beautiful analogy of this, because Mount St. Helens had a lake in its crater. That lake overflowed, it flowed down into the valley, and then it overtopped this elevated landslide deposit, and that's what creates this drainage canyon. It's from that mud flow that goes over the top of the plateau and then back cuts and creates this branching channel. And it's a 40th scale model of what we see at the Grand Canyon today. So it does have application to Grand Canyon, and even in secular circles, they're beginning to see this, because there just is no way for the traditional, the river cut the canyon slowly. That clearly is not what happened.
Cool. Well, if Zach will be here for a little bit afterwards, if you've got other questions. Thank you all for coming. Let's hear it for Zach. It's awesome to have somebody in our group who is in zealous pursuit of the truth in regards to the geology of the world and the way geology is created, the way the rock formations come into being, and he shares an awful lot of great information with us. So let's pray. Lord God Almighty, thank you for this presentation tonight, and to help us all to understand better not just what happened at Mount St. Helens, but potentially with the Grand Canyon and with other rock formations, Lord. We praise you and we thank you, and we thank you that you are the sovereign one. and that you are in control of all things. All praise and glory to you. In Jesus' name, amen. Amen. Don't forget, there's brochures over there if you're interested in the Wonders Center or the Genesis Science Network.
Just David Reeves.
Yeah.
He has a paper every 2 months. He sends